Hello everyone, I'm Aathira Dinesh and I'm here to take the topic Redox reaction on the basis of titration and limitations of the concept of oxidation number. Now before we get to it, let us know what is redox reactions and titration. Redox is a type of chemical reaction in which the oxidation states of atoms are changed. It is characterized by the actual or formal transfer of electrons between chemical species, most often with one species undergoing oxidation while another undergoes reduction. Titration. It is a process of chemical analysis in which the quantity of some constituent of a sample is determined by adding to the measured sample an exactly known quantity of another substance with which the desired constituent reacts in a definite known proportion. Basically, it is a commonly used laboratory technique which helps in the quantitative chemical analysis. It is it helps in the determination of an unknown concentration of already known analyte. Now, redox reaction on the basis of titration. Redox reaction. When the oxidation reduction reactions happen in a titration method, it is known as redox titration. In this technique, transfer of electrons occurs in the reacting ions present in the aqueous solutions during the chemical reaction. This is further classified on the basis of reagent used in the redox titration. This redox titration has three subdivisions that are permanganate titration, dichromate titration, iridimetric and iodometric titrations. Now, first let us know what is permanganate titration. Potassium permanganate is the oxidizing agent in this type of redox titration method. Maintenance of the solution is done with the help of dilute sulfuric acid. Moreover, the addition of sulfuric acid also helps to increase the hydrogen ions present in the solution. In this technique, the reagent has intense color due to the permanganate ion MnO4-. In the case, the permanganate ion acts as a self-indicator. The solution remains colorless prior to the endpoint. The equation of this redox reaction is given below. The result of the endpoint is noticeable when oxidation of the last of the reductant such as Fe2 plus or C2O4 2 occurs. At this point, the solution remains the first lasting tinge of the MnO4, that is pink color, appears. The concentration can be minimum of 10-6 mole L-1. This assures the minimum overshoot of pink color after the equivalence point. The equivalence point is where reductant and oxidant are equal with respect to the mole stoichiometry, or the total number of electrons lost and electron gained in oxidation and reduction reaction will be equal. The potassium permanganate titration helps in the estimation of oxalic acid, hydrogen peroxide, ferrous salts, oxalates, and more. However, it is very important to always standardize the solution prior to use. Now, dichromate titration. In this method, potassium dichromate acts as the oxidant in the acidic medium. It is necessary to maintain the acidity of the medium by addition of dilute sulfuric acid. The equation of this reaction is as follows. In this situation, there is no substantial autocolor change as seen in the MnO4- titration. Cr2O72- is not a self-indicator. However, Cr2O7- 72- oxidizes the indicator substance, the diphenylamine, soon after achieving the equivalence point, thereby producing an intense blue color. The change in signals the endpoint of the titration. We can use the potassium dichromate solution in titrations directly. This method helps in the estimation of ferrous salts and iodides. Now, iodometric titration. This is an interesting but common method. In this case, free iodine reduction to iodide ions occurs as well as iodine ion oxidation to free iodine occurs. The oxidation and reduction reactions are given below. The solution acts as an indicator. The use of this method is limited to the reagents capable of oxidizing iodine ions. One of the examples of such reaction is of copper. Here, 2 copper is added with 4 iodine and it gives Cu2I2, that is copper diodide plus iodine. The ability of iodine to produce intense blue color with starch as the substance and its capacity to react with thiosulfate ions forms the basis of this method. The specific reaction with thiosulfate is also a redox reaction. Iodine is reacted with thiosulfate and it gives 2 iodine plus S4O6 2 minus. In this case, I2 is insoluble in nature with water, but it remains in the solution in the form of Ki3 that contains Ki. After the addition of starch, the iodine in the reaction liberates as iodide ions, producing intense blue color. However, the color disappears on the consumption of iodine by the thiosulfate ions. The endpoint of the reaction is easily noticeable. Thus, it is easy to determine the concentration of the unknown solution by stoichiometric calculation. Now, the next topic is limitations of concept of oxidation number. Though the concept of oxidation number is widely used, at the same time it is very helpful in redox chemistry, yet it suffers from certain limitations. The limitations of the oxidation number are listed below. The main limitation of oxidation number is that oxidation number cannot be assigned a particular species. According to the classical approach, many reactions are called as redox reactions. However, it has been found that practically it is not possible to do the same by applying the oxidation number concept. The concept of redox processes have been evolving with time. This process evolution is continuing. In fact, in recent past, the oxidation processes visualized as a decrease in electron density and reduction process as an increase in electron density around the atoms involved in the reaction. Now, that was all about my topic. Thanks for bearing with me. Thank you.